Today, I will be talking on transport phenomena in furnaces, the role of convection and radiation in furnace design. Today, I will be taking role of convection in furnaces. Now, some introductory remark I had already given in my previous lecture, where I have said that convection heat transfer is associated with fluid motion. If you want to quantify the amount of heat transferred from one location to another, where motion of the fluid is involved, the first thing that one has to do is to know what is the velocity of the fluid. Unless you know the velocity of the fluid, you cannot quantify how much amount of heat is transferred from one location to another location when fluid is flowing. So, accordingly, in case of convective heat transfer, the fluid flow is most important. As I had already pointed out in my previous lecture, that if you want to predict or if you want to quantify the amount of heat transferred by convection, then there are two approaches. One approach is the differential approach or microscopic approach, in that you allow the fluid to flow through a volume element of delta x, delta y and delta z dimension, and then you do the energy balance and momentum balance. The whole idea of performing momentum balance is to know the velocity, and then the equation of momentum balance is coupled with equation of energy balance in order to get the amount of heat transferred. However, this is the most exact approach, but it requires a very long computer calculations, because the resulting equations cannot be solved analytically. They have to be solved by the use of numerical analysis followed by computational calculations. However, in most of the engineering calculation, what is important is how much amount of heat is being transferred. Without going into much of the details about the mechanism and so on and so forth. So, for most engineering calculation purposes, it is sufficient if we can provide a quantified information about the amount of heat transferred, and for that purpose heat transfer coefficient is an important concept. Heat transfer coefficient is an important concept. Now, according to this heat transfer coefficient, the amount of or the heat flow say between fluid and surface, that is equal to Q, that is equal to HC A into delta T, where HC is the heat transfer coefficient. C is heat transfer coefficient, and its dimensions are watt per meter square Kelvin, or it can also be expressed in terms of British thermal units upon hour, feet square, degree Fahrenheit. A is the area either in meter square or in feet square, and delta T is the temperature difference, between wall and fluid. Now, let us consider a temperature profile of a flowing fluid bounded by a cooler wall. That means, I will consider this is a cooler wall. Let us consider this is a cooler wall and fluid is flowing in this direction. This is distance from the wall, distance from wall. So, as the fluid comes in contact with the cold wall, so let me say this is the cold wall at temperature T0. So, as the hotter fluid comes in contact with this cold wall, which is at temperature T0, which is very much lower than the hotter fluid, then the fluid immediately in contact with the wall, its temperature decreases, and as such the temperature profile will look this particular way. And here we can characterize the different regions. Say this region is A, this is B, and this is C. So, now the region A is laminar sublayer. Laminar sublayer, as you know from the characteristic properties of fluid flow, as the fluid comes in contact with a wall, then the fluid in the immediate vicinity of the wall will have very low velocity, and its velocity will continuously increase as you move in the direction of the wall. So, B is transition zone. B is transition zone and C is the turbulent core. Is the turbulent core. So, the fluid is flowing in this direction. So, this is what the temperature profile of a flowing fluid which is bounded by a cooler wall. Now, as such, we have to characterize now the convective heat transfer. So, as such, we have say either free convection heat transfer, and the free convection heat transfer is associated because of the difference in temperature. So, here temperature difference causes fluid to move. Another mechanism is forced convection. And in the forced convection, we forcibly move the liquid, for example, by pump, or in case of gases by blower, by fan. So, here some sort of force is applied for the movement of the fluid to occur. So, this is in fact the forced convection. Now, both quantification of free or forced convection, it can be done in terms of heat transfer coefficient, the equation which was given Q HCA into delta T. Now, here HC is the heat transfer coefficient. Now, just a little information about heat transfer coefficient. Remember, heat transfer coefficient is not a property of the fluid. Heat transfer coefficient is an empirically determined constant by way of experiments. That means, you have a cold wall, allow the hot fluid to flow and record temperature as a function of time, and then invoke the equations to find out the heat transfer coefficient. Therefore, heat transfer coefficient is very much empirically derived constant. It depends on so many factors like geometry of the surfaces, like temperature gradient, whether it is a tube, whether it is a wall, whether it is a spherical shape. Everywhere the heat transfer coefficient will have a different value. That what I wanted to say is that depending on the system under consideration, for calculation of the heat transfer, you must search an appropriate empirical equation to calculate the heat transfer coefficient. Otherwise, you will be doing lot of mistake, simply because heat transfer coefficient is an empirically derived constant. It is not a physical property of the system. So, that is an important thing. So, now say heat transfer by free convection, in fact, based on the results of several experiments, empirically constant, that is heat transfer coefficient, has been determined, and it has been reported in the form of several correlations. For example, for free convection, heat transfer coefficient, that is represented by Nusselt number, it has been found to be a function of Prandtl number and Grashof number, where Nusselt number is say Hc d upon k, that is equal to a constant Cp mu, that is the Prandtl number, upon k d cube rho square beta g into delta t upon mu square, that is the Grashof number, and it is raised to the power some constant a, and the value of a and z has to be determined by experiment. Now, here d is characteristic dimension. Now, you must be careful for substitution of these values. Characteristic dimension. Now, in this particular form in which the equation is given, this is dimensionless. So, it does not matter whether you substitute the values in FPS system or SI system or MK system, but then if you choose MKs, then all values should be substituted in MK system in this particular formulation. K, thermal conductivity of liquid. K is thermal conductivity of liquid, mu is viscosity, rho density, beta is coefficient of expansion, Cp is specific heat, and of course, delta T is temperature difference. So, there are different types of correlation available. The one which I will be using for solving some of the problems based on free or forced convection heat transfer, that will be say NNU, that is equal to, let us put it the constant Z, NPR into NGR, that is equal to 0.25. So, this is the correlation for free convection heat transfer. However, here and there the value of the exponent and pre-exponent that vary. For example, the value of the Z, that is equal to 0.53. Now, some approximation can be made, particularly for gases which are moving in the furnaces. So, for gases and products of combustion, the Prandtl number is almost a constant value and does not depend much on temperature and pressure. Now, similarly, we can substitute the other properties, say viscosity or thermal conductivity, coefficient of expansion, specific heat of that of air, because air and POC, they are closely related in their properties. So, in order to calculate the values of heat transfer in the problems which I am going to give you, we will be using the following approximated correlation. However, for exact value, you can search from the literature or from the book and use that value. So, what I will be doing now, if I substitute the other properties like thermal conductivity, viscosity, density, coefficient of expansion and so on, say because air and POC they closely relate. So, I will be getting, say, for vertical plates, Hc can be calculated from 1.12 delta T upon D raised to the power 0.25. Now, mind you, here this is a dimensional equation, therefore, Hc, it has to be substituted. Hc you will get in watt per meter square Kelvin. So, delta T substituted in degree Kelvin and D in meter. Also, for large plane surfaces, we will be using Hc, that is equal to 1.25 delta T whole to the power 0.25. This is for the large plane surfaces. Now, the same in FPS system. In FPS system, for vertical, for say smaller vertical plates, this is also in the, for vertical plates smaller size, you can put it for the smaller size. Hc, that is equal to 0.28 delta T upon D. Now, here delta T is in degree Fahrenheit, D in feet, and Sc you will be getting in BTU, feet square, degree Fahrenheit, hour. For large plane surfaces, Hc, that is equal to 0.27 delta T raised to the power 0.25, here is also 0.25. So, these are the equations, some of them depending on the geometry of the furnaces involved and depending on the calculation that will be useful for furnaces. These are the correlation for heat transfer coefficient when there is a free convection. For example, the heat loss from the wall of the furnace to the surrounding, that is the case of free convection, then we will be making use of one of the correlation that I will illustrate at the time of problem solving. Now, similarly, for forced convection heat transfer, there could be several cases. For example, you have a cylindrical object. Or a sphere where fluid is moving or fluid is striking. This is, for example, object in a fluid stream. These are the example of forced convection heat transfer. Another example you can think of is that of the heat exchanger. See here, fluid in, here fluid out, hot fluid in, hot fluid out. This is typically a heat exchanger. Similarly, regenerator, recuperator, they are all the cases of forced convection heat transfer, and heat transfer by forced convection, the correlation is a Nusselt number that is equal to a function of Reynolds number and Prandtl number. Now, Reynolds number is entering because the liquid is moving. So, the correlation which we will be using Hc upon into D upon K, that is equal to 0.023 d g mu, which is the Reynolds number, into Cp mu upon K. This is raised to the power 0.4 and this is raised to the power 0.8. So, that is the correlation we will be using. Here G is the so called mass flux velocity. G is so called mass flux velocity. So, this is what the correlation we will be using for the determination of heat transfer by forced convection. So, that is what the evaluation of heat transfer by free or forced convection. For example, in case of free convection, the heat loss from the furnace wall. For forced convection, suppose the hot gases are flowing in a duct or hot gases are flowing in a heat exchanger. So, these are all the examples of forced convection heat transfer as related to furnace. The application of this equation we will see when I will solve the problem. So, with this I want to proceed the next mechanism, that is heat transfer by radiation. Heat transfer by radiation. Now, as you know, the energy is continuously radiated or emitted from the surfaces of all bodies in the form of electromagnetic waves of various wavelengths. So, that is in fact a mechanism of heat transfer, where electromagnetic waves of various wavelengths are involved depending on the temperature of the hot body. So, a hot body is always emitting the radiations. Now, the rate of radiation of heat from surface, it increases with the fourth power of the temperature. That means, heat loss or heat emitted by radiation is proportional to the fourth power of the temperature. Therefore, at high temperature, the heat transfer by radiation is a very important mechanism of heat transfer, because the heat is being lost or gained depending upon what you are dealing. It is the fourth power of the absolute temperature. And the famous Stephens-Boltzmann law is there, which relates the MEC power of a black body with the absolute temperature. Now, before that, the concept, now in radiation heat transfer, the concept of black body is important. A concept of black body is important. Concept of black body. Now, a black body, it absorbs all radiations that fall on it and reflect none. So, according to Stephens-Boltzmann law, the MEC power of a black body, the emissive power of a black body, say if we say EB, then we can say EB, that is equal to 0.173 into 10 to the power minus 8 T to the power 4, or you can also write down 0.173 T upon 100 raised to the power 4, where EB is the amount of radiant energy emitted per unit area. So, EB is the amount of energy emitted per unit area. That is, in fact, it is a flux and per unit time, that is a flux. So, in this form, this EB, the dimensions are BTU per hour feet square. Now, in this equation, T has to be substituted in degree Rankine, that is equal to degree Fahrenheit plus 460. That point is to be remembered. Now, in MKS system, EB, that is equal to 5.67 into 10 to the power minus 8 T to the power 4, that is also equal to 5.67 T upon 100 raised to the power 4. Now, here EB, that we will get in watt per meter square Kelvin. So, these are the say basic equation for the rate of emitting or the emission or the amount of energy emitted per unit area and also per unit time. So, an important thing in case of radiation is that black body is an idealized concept, just to represent and understand and quantifying the amount of energy radiated per unit time, per unit area. In fact, the behavior of all non-black bodies, is defined by the term called emissivity. So, emissivity is an important concept in case of radiation, which defines the amount of energy radiated per unit time, per unit area of any surface. That is what the importance of concept of emissivity. Now, so far we have considered the amount of energy radiated for one body. Now, let us consider the heat exchange, because in fact the amount of heat which is radiated by one body, it will fall on another body, that body gets heated up, it will also emit radiation, and the first body will also receive the radiation which is emitted by the other body. So, what I am talking about is, what we are interested is the rate of heat exchange between any two surfaces A1 and A2 which are black in nature. So, what we are interested in fact, the rate of heat exchange between two surfaces, say between two surfaces say of area A1 and A2. So, let me call this is surface area A1, this is area A2. Now, what will happen? A1 is a source and A2 is a sink. So, let me put A1 is a source and A2 is a sink. So, what A1 will do? A1 will emit radiation, that radiation will strike the surface A2. The amount of energy radiated per unit time, per unit area by area A1, that will be equal to sigma T1 to the power 4. Now, after a while, what will happen? A2 will be heated up, A2 will also begin to radiate, and A2 will also radiate, and it will fall on A1, What is the rate of emission? Sigma T2 to the power 4. So, net heat exchange between A1 and A2, that will be equal to net rate of heat loss from A1. A1 is the source and A2 is the sink. So, whatever amount of heat A2 will be receiving, it will also emit. So, the net heat exchange between A1 and A2, what we are expressing in terms of rate of heat loss from the surface A1, which is the source. So, Q, which is the rate of heat loss, that is equal to. Now, one more thing is important for the radiation, which is not in any other mechanism, for example, conduction or convection. What fraction of the radiation of the source is seen by the surface or the sink, only that particular fraction will be heated up. With this, what I want to say, that if the source is A1, which is emitting radiation in all the direction, if the sink A2 can see only a fraction of radiation, then that fraction of radiation is important in case of heat transfer by radiation. That means, the geometrical arrangement of the two surfaces is of utmost importance while describing or while quantifying the heat transfer by radiation, because it is a common sense. In radiation, that portion will be heated up which is seen by the radiating flux which is arriving from the source. So, that is where the rate of heat transfer or heat loss, it is defined in terms of sigma. Well, sigma is the Stephens-Boltzmann constant into F into A T1 to the power 4 minus T2 to the power 4, or that is equal to 5.67 into F into A T1 to the power 4 minus T2 to the power 4, or we can also write down 5.67 F into A T1 upon 100 to the power 4 minus T2 upon 100 to the power 4. So, that is the heat exchange between the two surfaces A1 and A2. Now, here you must now all the variables are known to you. T1 is the temperature of the source, that is, for example, this is the T1 is the temperature of source, T2 is the temperature of the sink, A is the area of the source, and F is a dimensionless composite factor. F is dimensionless composite factor. And for your information, it is the evaluation of F that is the most important part in case of heat transfer by radiation. Now, this F, it takes into account the geometric relationship between two surfaces, that is, how the source and sink are arranged, whether sink is bigger, source is smaller, source is bigger, sink is smaller, or source is inclined, and all sort of configuration that you can think of, that is taken into account by the so called dimensionless composite factor. F, it also takes into account the emissivities, and absorptivities, of two surfaces, and it also takes into account the geometric relationship, of two surfaces, to other reflecting or, for example, refractory surface. So, let me illustrate by a problem. Say a round duct a round duct 0.6 meter dia carries 100 meter cube per minute expressed at 25 degrees Celsius and 1 atmosphere pressure of preheated air at about 327 degree Celsius. The inside surface temperature of the duct, the inside surface temperature of the duct is 227 degree Celsius. Now, estimate A heat loss per running meter. And B drop in temperature of air per 30 running meter. So, this is typical. The gas is flowing in a duct. It has certain velocity because its diameter is given to 0.6 meter. The gas is flowing at the rate of 100 meter cube per minute. So, if I want to represent the problem, so this is the duct and it is carrying say 100 meter cube, carrying 100 meter cube per minute of gas at this temperature here is given to us 327 degrees Celsius. This inside temperature of the duct is given to you 227 degrees Celsius. So, as the gases flow, heat transfer will occur because of the difference in temperature. This is typically a problem of forced convection heat transfer because the gases are flowing at a particular speed. So, depending on its speed, the heat transfer or heat loss from the preheated air will occur, and that you have to estimate. Now, immediately it is a question of heat transfer by forced convection. So, we know that the heat transfer, that is Q, that is equal to Hc A into delta T. Hc is the heat, now Hc is the heat transfer coefficient. So, the value of heat transfer coefficient can be determined. Just now I have illustrated the correlation K, that is equal to 0.023 dG mu raised to the power 0.8 Cp mu upon K raised to the power 0.4. So, through this correlation we can find out the value of heat transfer coefficient. Now, what is required here in evaluating the properties of the fluid that is flowing, here in this example is air, one has to use the properties at the mean temperature of the fluid. So, here the temperature is 500 Kelvin and 600 Kelvin. So, we will take the properties. For example, we have to find out the properties. I am giving you, say, density, thermal conductivity, viscosity and kinematic viscosity. So, density is in kilogram per meter cube, K watt per meter Kelvin, mu kilogram meter per second, and kinematic viscosity in meter square per second. So, at 500 Kelvin and at 600 Kelvin, so density is 0.696, here it is 0.58, here it is 46.9 into 10 to the power minus 3, here it is 43.8 into 10 to the power minus 3, here it is 270 into 10 to the power minus 7, here it is 305.8 into 10 to the power minus 7, here it is 38.8 into 10 to the power minus 6, here it is 52.7 into 10 to the power minus 6. So, the mean value can take, say, density, it becomes 0.638, here it is 43.8 into 10 to the power minus 3. Now, here this value is 46.8. So, mu we do not need because I took the kinematic viscosity. So, it is 46.0 into 10 to the power minus 6. I write once again the value of K, that is K, which is watt per meter Kelvin. The value of K is 40.7 into 10 to the power minus 3, and here it is 46.9 into 10 to the power minus 3. So, the mean value is 43.8 into 10 to the power minus 8. So, that is what we know, all these values. Now, what we have to do? We will substitute in the formula to determine the heat transfer coefficient. So, I will just do for you, so that C into 0.6 divide by 43.8 into 10 to the power minus 3, that is equal to 0.023, 0.6 into 100 upon 60 into 46 to 10 to the power minus 6 or 0.8, and Prandtl number is 0.74. So, 0.74 s to the power 0.4. So, if I solve this equation, I will be getting Hc, that is equal to 4.39 watt per meter square Kelvin. Now, if I want to find out the Q, which is the heat loss per running meter, so I have to multiply by area, that is the pi d L. So, that will be heat loss will be equal to 827 watt per running meter. Per running meter, you can find out Q, that will be equal to Hc into 2 pi r L into delta T. So, you can find out from this. Now, next we have to find out what is the drop in air temperature per 30 running meter, because the drop in temperature is important. Suppose you are integrating the flow of air with some furnace which is using preheated air, then it is important for you to know what is the drop in temperature. So, in fact, this heat loss which is 827 watt per meter is in fact the sensible heat lost by air, is it not? Because air is flowing at certain speed, and in a 1 meter length it has lost around 827, that means it has lost is sensible heat. So, heat loss is equal to the sensible heat loss of air. So, once we know this, then we can see m Cp delta T, that is equal to 827, and from here we can determine delta T, that is equal to 0.45 degree per minute, and for 30 meter the drop in temperature would be 14 degrees Celsius. So, this is the answer, and here this is the answer. So, you see now how easily one can estimate the heat loss in case of forced convection heat transfer. Now, similarly, other type of problems can also be tackled by utilizing the concept of heat transfer coefficient. Now, remember, the concept of heat transfer coefficient is easy to perceive, but the most important thing is to find a suitable correlation. If you are unable to find a suitable correlation, then the values which you will be calculating, that will not be representing to the problem under consideration. So, the most important thing in utilizing the concept of heat transfer coefficient is only selecting an appropriate correlation to estimate the heat transfer coefficient. I will repeat once again, because heat transfer coefficient is not a property of the system. It is an empirically derived constant, and its value must be carefully determined through using a suitable correlation that is suiting, or that is rather representing the problem under considerations.